This item is quite big, so I'll start off with a face video in the live stream area. I do stream on Twitch for reference, bigclive.com on Twitch. Now, during the peak of the pandemic, there were lots of quack products and real products being sold online. And one of the real items, and I featured a version of this that was in a much bigger box. This is really strangely small. But one of them was the tabletop UVC germicidal lamp that puts out huge quantities of UVC energy and sterilizes every surface in your room and also puts out ozone, which gets into the bits that the light can't get to. So now that the peak of the pandemic has passed, I mean, it's still sizzling in the background. The health industry can tell you all about that. But now that the peak of it has passed and the novelty has worn off, the companies are now dumping their stock on eBay and getting rid of what's in their warehouses. So I'm just unpacking this and we'll take a look at what we've got here, because this is one of the UVC lights and it was being sold at a price of £10, inclusive of shipping. And they shipped to here, which is an odd location, which is good. And they didn't immediately mark it as not shipping to the Isle of Man, which is even better. So what we have here, we have a remote control, which has just dropped out. We have batteries for the remote control. Oh, they're fake Duracells, complete with the little fake test strip on the side. We have the tube. The UVC tube, quite a big one, and it looks intact, which is nice. We have the base for that tube, and we also have the surround. Okay, now we've seen it unpacked, so to speak. Let's take it back over to the bench and we'll take it apart and see what's inside it. We'll give it a test as well. We'll also check the UVC output with a meter. Let's do that right now. Back at the bench, I have installed the tube into the unit, but I'm not going to put in the frame because it looks like it's going to be a one-way trip clipping this in. It might not come out easily. And I kind of prefer it just with the exposed tube. I think that's more for protection. So I have preheated this so we can get a good look at it straight away, noting that this will put out UVC light. It's extremely bad to look at with your bare eyes. I've got glasses on that will protect me from direct light going in, but it can find its way either side of the lens, so I have to be careful of that. But I'm turning it on at the moment, and initially the power meter shows 1.1 watts. That is just the remote control. If I press the on-off button, it starts powering up, and I'll let it come up to... No, I won't leave it too long. That jelly beaning effect is interesting. It's common with fluorescent tubes. If I get my UVC meter now, and I have tested this after letting it warm up for a while, this is a real UVC meter calibrated for mercury vapor tubes. And if I put it at the prescribed distance, hold on, I'll do it right now, of 380 millimeter apparently. I'm not sure why 380 millimeter or 15 inches, but let's do that. When I hold it that distance, he said, smacking something with the thing, it shows 210 microwatts. That's quite a lot. I'm going to let it warm up again and then we'll test it and see if it goes any further than that. So I'm going to get out this area before I suffer eye damage. So I'll be back in a moment. Okay, right, I've let it warm up and I am getting huge readings when up close, but at the prescribed distance I'm getting about 400 microwatts a centimetre squared. So per square centimetre, that's a decent output. That is a very high output. I'm going to turn this off now because I do not wish to be exposed to much more UVC. It's not good for your eyes or skin. So I shall unplug this, get this out the way, and then I'll put the tube out the way so I don't break it. Totally worth it for the tube on its own because that is an expensive tube. It did say it was a 38 watt tube. I measured that around about 26 watts. It says UV386. Maybe they're just underrunning it. I'm not sure. I shall put this somewhere safe. I have put it somewhere safe. Let's open this. Hopefully, while making this video, this doesn't clip together very well, does it? Because this isn't screwed it's clipped together, and it's not clipped together well. It comes apart very easily. Useful for us, not great for safety, or rather things like this were screwed together. What do we have? We have a relay and a dropper capacitor, and a standard driver, a standard ballast out of a compact fluorescent lamp here, going to the socket. Okay, we'll tell you what, I'll take these items out. Oh, actually, you know what? Look at this. See the little white wire here? That's the antenna. And that is reference to the mains in this unit, and it's just randomly tucking over next to the circuit board over here. That's not great. I'd rather they put a little bit of insulation over the end of that. But they haven't. Anyway, I shall pop these circuit boards out, and we'll reverse engineer them and see what we can find. One moment, please. Double reverse engineering is complete. Let's explore. I am more relaxed now because I did not enjoy making that first part of the video in front of a fairly high output UVC tube. Not a good thing to have in your vicinity. Anyway, let's take a look at the back of the remote control first. And this turns out to be a 2-channel remote control. It's got a position for another relay, and it's using a capacitive dropper. Most of the tracks in the back here are the marshalling of the power. The 2 lives also feeding the common contacts of the 2 relays, but there's only 1 relay in place, and then the neutral going down to a little inductor here, which is quite unusual. You'll see that on the other side of the circuit board. And then some power marshalling for the connections to the transistors for switching the relays, their coils, and also for distributing the 12-volt rail and the 5-volt rail, because it's a dual voltage system. And then a big ground plane. Let's take a look at the other side of the circuit board. It's much more interesting. Interesting and just a bit weird. Here's the relay. There's where I removed the capacitor for the capacitive dropper, just so we could take a look at the circuitry better. There's a bit of direct fire, classic capacitive dropper with a 330k resistor across it. There's the inductor, which is quite odd, but it's in line with the AC in, as I'll show you on the schematic. And then oddly, there's a resistor in series with the Zener diode for the 12-volt rail. But then there's another resistor down here and another Zener diode down here. And it's odd that they've mounted them there and here because they're actually both in parallel. But that resistor will probably share the load across them, as you'll see. Bit filtered capacitors, a current limiting resistor, 300 ohm, and then a 5.1 volt Zener to give the 5 volt supply over to the rest of the circuitry with this odd chip here. This is a radio receiving chip that decodes the signal and puts out a single data bit to the dedicated, this is a microcontroller that has been rebadged by FMD with their software in it for controlling the outputs. I wonder if one of these 3 extra pins is for putting it into pairing mode. But this one's quite notable, and you'll see in the circuit board, because it is not using a crystal like many of them do, or a resonator. It's actually using a tunable inductor. I thought that was a capacitor initially, but when you see it from the side, it's got the windings. Can you see it from the side here? Little windings there. And you can tune it by screwing this screw, which moves the metal slug down into the windings, which actually changes the inductance. So let's take a look at the schematic of this. It's a part of a schematic. There is a manufacturer's datasheet with an error on it. We'll look at that in a moment. Here's the incoming supply, the live and neutral, with the live being switched through the relay. Just double checks it is the live being switched through the relay. Yes, it is the live being switched through the relay. And the common neutral going out to the loads. There's the 470 microhenry inductor on one leg going to the bridge rectifier, and there is the 1 microfarad dropper capacitor with its discharge resistor on the other leg. That then goes to a smoothing capacitor and filtering capacitor, and here's the double Zener diodes that are in different bits of the board. 68 ohm resistor and a 12 volt Zener diode paired up. This will spread the load. It means they're not dissipating as much because it's kind of shared between them. Then that 12 volt rail goes over to the relay to be switched by the transistor to the 0 volt rail to turn the relay on with no snubber diode, no back EMF flywheel diode, which is a bit naughty. But that 12 volt also generates the 5 volt supply via this 300 ohm limiting resistor and a 5.1 volt Zener couple of filtering capacitors, a 2K2 resistor, 2200 ohm resistor to presumably bring that rail down quite quickly when the power's taken away, because if it goes down too slowly, it can cause problems with the microcontroller locking up. Here is the RF module, and I'll show you more about that in a moment. It's got an antenna. The antenna for the RF experts is 195 millimeters long. The microcontroller receives the data from the RF decoder module, and then there's a 300 ohm resistor to the base of a standard J3Y NPN transistor to limit the current into the base that then switches the relay. Now, if you look at the datasheet from the manufacturer of this chip, I have augmented it in bits. There's the error. They showed this connected to ground. It's not. There's the ground there, and this one wasn't shown as connected to ground. That is the correct connection to ground, and it certainly tallies up the circuit board. The antenna comes in. There's a 105 picofarad capacitor. That was the only one that wasn't part of a circuit, so I could measure it. And then we've got a little capacitor inductor parallel pair here, possibly, well, probably for filtering. And then we've got some other capacitors for internal filters here. One going to ground, one going between the two filter connections. We've got the positive supply, and then we've got the oscillator, which is that little circuit there with the capacitor in parallel with that tunable inductor. And then the output goes out to the microcontroller. Okie dokie. Next thing to look at is the lamp driver. I shall put that out the way. Now, the lamp was being driven at roughly, I'll put this round this way, it makes more sense to me. Is that the best way to do it? Maybe I'll do it that way. Here is the back of the circuit board with all the components drawn on. Let's zoom out just a tiny little bit. Tiny little bit. And it is an absolutely standard compact fluorescent lamp circuit. It's literally textbook. If you see little bits of copper cover, the solder resist missing, it's because, oh, it was so hard getting that double-sided foam tape off. We have in this, we've got a common little toroid core here. That's the feedback transformer. Oh, I'll zoom down that so you can see it. Common little feedback transformer, which is in series with the main inductor that limits the current out to the, I'll just focus up on this to be honest. That's better. This limits the current out to the tube, but this is in series and this provides the feedback to the two transistors. And interesting, they're both NPN because each effectively has that old transformer feeding its base. Back down to the schematic. Well, not the schematic, the drawing we go. I shall zoom back out again. So there is, could have just shown you here, there is the inductor. There's a bridge rectifier based on discrete diodes, 1N4007. Here is a big fat 10 microfarad, 10 microfarad, 450 volt. They're playing safe capacitor. Keep in mind that this unit is normally designed to go in the base of a compact fluorescent lamp where it would normally be baked to the point that everything would go brown. But in this case, it's actually got quite a nice area and cooling effectively to dissipate some of that heat. So this is going to have a pampered life versus other ones. There is a start circuit in this. The start circuit involves this capacitor charging up and this diac pulsing this transistor to turn it on when it's in a stable state, when it's not actually running. One of these capacitors is used to limit the current in each half cycle, and the other one is used to ration the current through the heaters in the tube, as I'll show you in the schematic. Let's go straight to the schematic. It's fairly complicated, but also very, very simple for what it does. Am I going to fit that in? Yes, I'm going to fit that in. I'll move it up a little bit. Here's the incoming AC supply. I'm just going to make sure I'm totally focused down onto here. Bridge rectifier based on 4 discrete diodes and the big 10 microfarad 450 volt capacitor. We have a 1 nanofarad capacitor. Not sure what that's about. But we also have a resistor here, which I've not drawn the value in of. That's a bit remiss of me. Let's do that right now. So that is a 470k resistor. 470k, quite a high value. Others have mentioned that before it's struck, the circuit may actually run at higher frequency. I'm not really sure to actually put more current through this. It's hard to say. I'm not really sure. This is more sort of like for the analog electronics experts. But initially when you turn it on and it's not running, current will flow through this resistor, and it will flow through this resistor, and it will charge this capacitor up. Once it reaches about 30-ish volts, this diac will trigger, and it will give a pulse to the base of this transistor, and that starts the circuit oscillating. When the circuit is oscillating, say for instance, this one turns on, it is pulling current from positive via this capacitor through the tube, and through this inductor, the main inductor, 3.3 millihenry, and through the little feedback transformer. And in doing so, because the current's flowing through the feedback transformer, it induces current in this winding here, and it keeps the transistor turned on until it reaches the point that no more current is flowing that circuit. Then the whole lot collapses and it goes in reverse and drives that transistor. But also notice that it's charged up this capacitor, it's fired the diac, but now it's running. The current is still flowing through here potentially, but because this is being pulled down to the 0 volt rail by this transistor, and there's a diode here, effectively just keeps discharging this capacitor. The capacitor can't charge up, so it can't fire a rogue pulse to this transistor while that one's turned on. There are diodes between basically the emitter of each transistor and after its 1 ohm resistor and the base. Now, what is the 1 ohm resistor for? Is that just to limit peak current? It may well be to limit the current to sensible levels. And there's a 22 ohm resistor in the base circuit with that tiny little 2.5 turn transformer. It's quite surprising how few turns are needed to turn these transistors on. 100 nanofarad in the series, the 4.7 nanofarad between the two heaters, so that current, even if the tube isn't struck, current will flow through the heaters, through that capacitor, and then I guess ultimately, initially, there's a higher open circuit voltage, and once the tube's struck, that will reduce the amount of current flowing through there. That's it. Seems so simple. It wasn't simple to reverse engineer, but that's what happens. Not sure what that little capacitor's for. Maybe it's to give it a kick at the start to try and get it running. Maybe that's an initial attempt at starting the tube, but then the diac is just the option. Some circuits don't have the diac. They just rely on natural, just starting randomly which transistor runs first as the winner, so to speak. But that is it. Now, the tube, it did have the sizing of a 38 watt tube, as they state the power rating is, but it seemed to be running at about 26 watts. And 26 watts is a fairly standard value for the next size of tube down, but there was major variations between the tube sizes. All the ones I looked at all seemed to have slightly different sizes. But there we have it, the UVC germicidal light. They've made it simpler. They've just used a standard module. The other one had a little rectangular ballast circuit board in it. But ultimately, not much difference, just that remote control. I'm not sure how secure that remote control is. Wouldn't want to leave the unit plugged in while I was in the same room, just in case somebody used a remote control externally and triggered it. But that's it. It's just basically the remote control receiver, the driver for the tube, and then the tube itself plugged into the standard base. It's very basic, very standard, but they do have their uses. Just remember, as always, UVC energy will cause problems with your eyes. It causes ocular, is it conjunctivitis? No, that's the... I'm going to have to look that up now. I'm going to have to look up the name for that. One moment, please. Photokeratitis. Yeah, I've not said that word in a long time. Basically what happens if your eyes get exposed to this particular wavelength, the longer wavelength of UVC, 254 nanometer, it can damage the surface of your eye, and that manifests itself later. It doesn't happen when you're doing it. That's why I was getting the heebie-jeebies after, like, having that tube lit for a couple of takes. But what happens is later at night, if you've been exposed to welding arc flash or discharge lamps, the light output from them, that includes like theatre fixtures and these UVC tubes, then what happens at night is you wake up feeling like someone's thrown a handful of sand into your eye. There are various remedies for this. You can get anesthetic eye drops, because they will get better, but it'll take, maybe, depending on your exposure, you might be fine in the morning, as I was when I did accidentally overexpose my eyes. But it can sometimes take a few days and it's very uncomfortable. The welder's trick is to put, and I can't recommend this, but the welder's trick is to get some juice from a potato and put the potato juice in your eyes. I'm not sure what that does, but it's putting rogue things in your eyes. But that's it. Also, avoid exposing skin. Keep humans, animals and plants that you value, or delicate bleachable fabrics, out the way of UVC light, because its job is to destroy. That's its purpose, and it does it very well. But there we have it, an interesting and cheap sell-off of all the bulk stock from the pandemic. Quite good if you're wanting some of those tubes.